Hello everyone. There's currently about 10 minutes left in the Texas Auburn game. We're tied at 58-58. But I'm making this video because I suspect y'all have less time to work in your homework in class because we lost the days because of the weather. And so instead of me helping you in class in the homework, here's this video that you can reference to help you with your homework. Okay. So the due date for the exam is not changing, but you have to know what's on the homework so you can do well on the exam. So here we go. So number one. So it's an Atwood machine. It's like the pulleys. We've done pulleys in the past, right, where you've drawn your free body diagram for each object, write your net force equation, and then solve for what you have to solve for. But this one's going to be a little different because in the past, I've told you that pulleys are massless. But now, right, the pulleys have mass, and we have to account for the rotational inertia of the pulley, right? Because the pulley is harder to turn, then it will accelerate slower. But this process is going to be the same, where you'll draw your free body diagram, write your net force equation, and then solve. So we can draw a free body diagram for M3, right? So M3, there is gravity going down, so I'll call that M3G. And then there is a tension going up, right, because it's on a string. So I'll call this tension T1, right, T1. And I'll call this tension T2, and I'll call this tension T3, right, because it's three different parts of the string. So then we'll write our net force equation. So the problem tells you to use down as negative. I know it says down, but what they really mean is that if it goes in this direction, it'll be positive. Oh, I think it's a negative. Down is positive. So anything that was spin counterclockwise will be positive. So M3G, right, that makes M3 go that way. So that will be positive. So our net force equation, F net, is equal to MA. It'll be M3G minus T1 is equal to M3A. And we can do something very similar for the other hanging mass, M4, right here. There is gravity, M4G down. That's a 4, that's a G. And then there is tension, but it's a different tension or a different part of the string, T3 going up. So then F net is equal to MA. So T3 will make it spin that way, right? T3 goes up, it'll make M4 spin that way. So T3 positive, so it'll be T3 minus M4G, and that will be equal to M4A. So that is the same process that we've done in the past, right? But now we will have to do something similar for the pulleys. So instead of doing a net force equation, we'll do a net torque equation, because the pulleys will spin and they won't actually move in a straight line. So for M1, it'll look like this. So there's my M1. So it has R1, right? I'll call it M1. There is T1 going that way. And then there's T2 going that way. So T1 will make it spin this way. T2 will make it spin the other way. So then T1 will be positive. T2 will be negative. Okay, so torque. So instead of F, we'll use torque. Instead of M, we'll use moment of inertia. Instead of A, we'll use alpha. And torque is also a force perpendicular multiplied by radius, or the distance away from the turning axis, which is just a radius that we're given. Okay, so torque, T1 is positive. So T1, that's our force that's perpendicular. And then our radius is just R1 minus T2, R2, is equal to I alpha. And I, for a mass concentrated at the rim, that is a hoop, I think. Yeah, it's a hoop, right? Because hoop, or a ring, all the mass on the outside. So that's just mr squared. So T1 R1 minus T2. Oh, why did I put R2? That should be an R1. So T2 R1 is equal to M1 R1 squared alpha. Okay, but if we're looking for acceleration, right, what's nice about, they ask specifically for the acceleration for the hanging mass on the left, but everything's like connected together, so they'll all have the same acceleration. So we want acceleration, that's A, but our equation is alpha, so we gotta turn that A, or we gotta turn that alpha into an A. And so the way we do that is with this equation right here on your formula chart. A is equal to R alpha. A is equal to R alpha, and that means alpha divided both sides by R is A over R. So instead of alpha, I'll put A over R. So it'll be T1 R1 minus T2 R1 is equal to M1 R1 squared. Instead of alpha, it will be A over R. And so then we have two R1s on top, one R1 on the bottom, so like one of these is gone. And then now there'll be like one R1 in every single term. So then the R1s cancel out. So it's really T1 minus T2 is equal to M1A. And then you can do something very similar for the other pulling. So that's M2. Right, M2 looks like this. Right, so there's T2 going this way. There's T3 going that way. And it has mass of M2, and like that radius is R2. So then the net torque, T2 makes it go in the positive direction. T3 will make it go that way, so that's negative. So then T2 R2 minus T3 R2 is equal to I2 alpha. And then instead of I, we'll put mr squared, and instead of alpha, we'll put A over R. So T2 R2 minus T3 R2 is equal to I, which is now, right, I is equal to mr squared. So mr2 squared, and then alpha is A over R. So then A over R. And one of these R's is gone, and then there's an R in each term. So it really becomes T2 minus T3 is equal to M2 to A. All right, Auburn just hit 3. Okay, so we got 4 equations, right? I'll circle them in black. We got 1, 2, 3, 4. Yeah, so we don't know T1, right? We don't know T1, we don't know T3, we don't know T2, we don't know T1, or we don't know A, right? But that's only 4 things that we don't know. But there's 4 equations. So you can use a system of equations to solve for your unknown variable. You can use whatever method you want. You can use substitution. You can use a matrix. I've seen Wyatt use his calculator. He has some function thing, which you can do too, I guess. I guess it's illegal. I will use elimination because it's my personal favorite. So I will just rewrite the equations so it's easier to see. And T1 minus T2. So if you look at our 4 equations, I have a negative T1 here, positive T1 here. There is a positive T3 here, negative T3 here, negative T2 here, positive T2 here. So then that means if I like add all my equations, all the tensions will be gone, and I'll just have everything that I know except for A. So then when I add, it's M3G minus M4G is equal to like M1. I guess it doesn't really matter. To M3A plus M4A plus M1A plus M2A. So then I'll factor out an A on the right side, right? Because there's an A in every single term. And then I'll divide on both sides. All right, that's just a number. So then now we have our equation for A. And then we know all the masses. All right, they tell you right here. Right, they tell you the mass of the wheels and the mass of the hanging masses. Oops, what did I do? Right, your numbers are different. Don't use my numbers. So then we can like plug everything in and you can solve for A. But this is the work that you have to do to get to your acceleration. So if you show your work and you just have this equation, then you're not going to get the credit because you have to draw a free body diagram, right? You have to draw your net force equation, net torque equation, and then you can do the algebra. It's like this is the physics part, this is algebra. You have to show all of it. That's number one. So then number two is a merry-go-round, and there's some force. We have to find the kinetic energy of the merry-go-round after some time. Okay. So I don't know about you, but the merry-go-rounds that I went on as a kid, there's one at the zoo. They only spin and they don't move. So the energy of the merry-go-round is just rotational kinetic energy. Right? So that is equal to 1/2 I omega squared. So that means if we know I, we know omega, right? We just plug it into our equation and we can solve. It's like this is our goal. We want I, we want omega. So to solve for I, it tells you to use a merry-go-round as a solid cylinder. So I for a merry-go-round, or my solid cylinder, is solid cylinder 1/2 mr squared. So I is equal to 1/2 mr squared, right? We have the radius, right here. So that's easy. So this is R. Your R is not 1.3. We don't know M, but that's okay. Because if you look, right, they give you the weight of the merry-go-round. Yours is different. Mine's 826. So this is weight. I'll call that W. And you know from your skills check and literally everything we've done so far this year is that the weight is equal to mg. So if I want to solve for mass, right, divide both sides by g. So your weight divided by little g is equal to mass. So you know this, right? That will go here. You know R, so you can solve for I, right? Once you know I, you can plug it into that equation and you can solve for omega. Okay, so then we gotta solve for omega. This one can be a little tricky because like, right, you would think you would use one of the equations with omega in it, right here. Right, if you want to use one of these, right, they all have alpha, right? So let me just like clear out this up. Right, we don't have V, so we can't use that one. So we got to use like one of these. So I would start with the easiest one. This looks like the easiest one because we know our initial angular velocity is 0. So this is 0. We're given the time and we're looking for this. We're looking for omega. So then we have to solve for alpha. We got to solve for our angular acceleration. Also, our defense is terrible. Okay, solve for angular acceleration. We have another formula with angular acceleration in it. So that is our torques. Oops. Oh, I guess I didn't copy the back of my formula chart. I'm on the back now. But your formula chart has this equation on it. It says torque is equal to I alpha, right? That's Newton's second law for rotation. And then we have our equation that we wanted is equal to initial plus alpha t. Okay, so our initial angular velocity is 0. And we know our time, right? Our time is right there. Mine's 2.93. Yours is different. So if we know alpha, we know time, we can use this omega, put that into our equation for rotational kinetic energy, and then you can solve. Okay, so torque. Torque is force perpendicular times radius. We know radius, and you just solve for I, so we're going to find torque, so we can solve for alpha. So if you redraw the picture, this is the top view of a merry-go-round, has some radius r, and then there's a force applied tangentially. That should be a right angle. I'll call that F. So my F is 66.6. Your F is a different number. So then you just, it's already, right, tangential. So it's already perpendicular to your returning axis. So you just gotta multiply by r. So then, right, you can solve for torque. After you solve for torque, you know I already, right? It's the same number you've used before. You can solve for alpha. So then T over I is equal to alpha. Once you solve for alpha, you can put it into there. And then you'll solve for your angular velocity. Once you know your angular velocity, you'll just use it in the equation for rotational kinetic energy. You'll get a number and you'll put that into Quest. But I'm not gonna do it because like there's no point in me like doing mine because like everyone has a different number. So I'm trying to teach you like steps to how to do it. So we started with our formula for rotational kinetic energy. Right, we can realize we solve for I pretty easily, right? Because it is a it's a solid cylinder, and there's an equation for I for a solid cylinder. So once we know I, we have to solve for angular velocity, but we can't do it directly. So we had to solve for our angular acceleration and multiply that by our time to then solve for our angular velocity. And then we just put in the formula and you can just like get a number. So that's number 2. Okay. Number 3. Purple. Actually, we're down all to orange for UT. Okay, so it says a sphere rolls along a horizontal smooth surface at a constant linear speed without sloping. We want the ratio between the rotational kinetic energy and the sphere's total kinetic energy. So the sphere is spinning, it is rolling, and it's moving at some linear speed. So the total kinetic energy, right, that would be the rotational kinetic energy and the translational kinetic energy, like add together. Right? Total means to add. And then what the ratio, so ratio means to divide. So that between the rotational kinetic energy, so I'll take my rotational kinetic energy, and then I'll divide that by my total kinetic energy. And whatever number I get, that will be my answer. Okay, so the formula for rotational kinetic energy is 1/2 I omega squared. The formula for translational kinetic energy is 1/2 mv squared. So that I'll just solve for them individually, and then I'll just put it into my goal equation, and then I'll get a number. Also, we just break that 3. Okay, so K rotational is equal to 1/2 I omega squared. Yeah, it looks like Texas is gonna lose, but that's okay. So I for a sphere is, I don't remember, but it's on my formula chart. I is for a sphere, where is it? Wait, where did it go? Oh, right here. I is for a sphere is 2/5 mr squared. So then I is 2/5. So then K rotational is equal to 1/2 times 2/5 mr squared omega squared. Okay. And then K translational is just 1/2 mv squared. But if you want to like put it in the ratio, it's easiest if you have all v's or all omegas. So we have v and omega, so you would just like choose one of them to convert. And the formula you'll use to convert between all v's and omegas is right here. V is equal to r omega. And so then you can choose, right? You can do v over r is equal to omega, but it's already in this form, so I'll just like substitute r omega in for v. So my translational kinetic energy is 1/2 m. Instead of v, I'll do r omega, and then the whole thing squared. And so the common mistake people do there, they only square one of them, but if it's parentheses, like everything inside the parentheses is squared. So it's really 1/2 mr squared omega squared. Okay. So then once you have that, you can just put it into your ratio. So we want K rotational on top, and we know K rotational is 1/2 times 2/5, which is just 1/5. So I'll just rewrite it, K rotational over k rotational plus k translational. So we'll do 1/5 m r squared omega squared. And then on the bottom, right, it's k rotational again. So 1/5 m r squared omega squared plus translational, which we solve for 1/2 m r squared omega squared. So now it becomes like an algebra to simplify our fraction. So then 1/5 plus 1/2, right, the common denominator is 10. So 1/5 I will write as 2/10. 1/2 I will write as 5/10. So the bottom it's 7/10. Like 2/10 plus 5/10 is 7/10. So then 1/5 m r squared omega squared and 7/10 m r squared omega squared. Right, m r squared omega squared on top, m r squared omega squared on the bottom. So then it's 1/5 over 7/10. So then you do whatever you normally do to divided fractions, right? Keep, change, flip, or whatever y'all called it. So that's 1/5 times 10/7. So then that is 10 over 35, which you can simplify, divide by 5. Then you get 2 over 7, which I believe is right here. But look at all the work you have to do. I'm going to show the work. Okay, next question. I'll do purple. Okay, so it is a basketball, and it is rolling down some incline, and we gotta find the time it takes. Cool. Okay, so let's draw a picture. So there's my incline. My angle is 59.7. Yours is something else. I'll call that theta. And it rolls down some distance. Right, there's my basketball. And it rolls some distance. I'll call that, I don't know, I'll call it x. And it has like a diameter. I'll call that little d. Right, so this is d. I call that x. I call this theta. And we want to find the time it takes to roll down. Okay. So if you imagine it's like a car and it goes some distance, now it looks like a one-dimensional kinematics equation. So if I gave you like the initial and final velocities, right, you would use one of the equations for kinematics to solve for the time it takes to travel that distance. So here, right, we know our initial velocity is 0 because it starts from rest. Right, starting from rest. So then if you know the final velocity, then you're able to use your kinematics to solve for the time it takes to travel that distance. So to solve for the final velocity, right, we're going to use our conservation of energy, right? Because also like a hint that will let you know whether you use conservation of energy is if like there's a change in height. If there's a change in height, there's a change in energy. So I'll start by drawing my energy pie charts. So I'll do that in blue. At the very top, there is potential energy, gravitational. And then at the bottom, right, our basketball is moving and it is spinning. So there's two types of energy. There's translational kinetic energy and rotational kinetic energy. So in our energy conservation statement, we will write energy at the beginning, potential energy, gravitational, equals energy at the end, translational, plus rotational kinetic energy. So then on the formula chart, the formulas for each of them. So UG is equal to mgh. Translational kinetic energy is 1/2 mv squared. And then rotational kinetic energy is 1/2 I omega squared. But if we're looking for a v, we want to turn that omega into a v. So then, oh, look at that. So v is equal to r omega. So then we'll just substitute that into our equation. So our mgh is equal to 1/2 mv squared plus 1/2 I omega squared. But I'll substitute, instead of write omega, I'll write v over r, right? Solve for omega. So omega will be v over r. So mgh is equal to 1/2 mv squared plus 1/2 I v over r. Okay. And then I, it tells you to use your basketball as a thin spherical shell. So I for a thin spherical shell, not to be confused with a solid sphere. All right, sphere specific. Thin spherical shell is right here. So it's 2/3 mr squared. So instead of writing I will write 2/3 mr squared. So mgh equal to 1/2 mv squared plus 1/2 times 2/3 mr squared, and then v squared, v over r whole thing squared. So I'll square the v, I'll square the r, and there's my equation. So then if you look, I got 2, right, r squared on top, r squared on the bottom, so those cancel out. So it's really mgh is equal to 1/2, and then plus 1/2 times 2/3, just 1/3, mv squared. Oops, I forgot the mv squared. So 1/2 mv squared. 1/2 mv squared plus 1/3 mv squared, right? So the common denominator between 2 and 3 is 6. So 1/2 is 3/6, 1/3 is 2/6. So when I add together, it's 5/6. So mgh is equal to 5/6 mv squared. M's on both sides cancel out, so gh is equal to 5/6 v squared. We're solving for v, so then I'll multiply by 6, divide by 5 on both sides, and then I'll take the square root. So it'll be square root of 6/5 gh is equal to v. But then we get another problem, right? Because we don't know h, right? Because h is like this distance that it goes, and we're not given that. But we know that it's a right triangle, so I'll redraw my triangle. So like this distance is x, this is h, we know our angle. That means our height, right, that's the opposite side. We have the hypotenuse, so x sine theta. If you want to go from the very beginning, go right, sine theta is equal to opposite over hypotenuse, and then solve for hypotenuse, like multiply by x, right? So x sine theta, h, you get the same thing. So then you'll get a number for h, right? X sine theta, you'll put that into there, and then you can just solve for your velocity. Okay, so then once you solve for your velocity, unfortunately, that's not the answer. We're looking for the time it takes to travel. So with kinematics, the average velocity is equal to like your displacement divided by your time. We know our displacement is x, right? It traveled that distance down. So then the average velocity, right? You got two numbers, you can average, is your final, so your final velocity plus your initial velocity divided by 2. And then our change in x, I just call that x. We know the time. And your initial velocity is 0. So it's just your velocity that you solve for, like this v, goes there, divided by 2. So then v over 2 is equal to x over t. So then you just multiply by t. So like your time times your velocity divided by 2 is equal to your distance, which is what we want. So you solve for v, your velocity, using your conservation of energy. All right, multiply that by your time, divide by 2, and then you get your distance. Or no, we're solving for time. So I guess I'm gonna do a little different. So v over 2 is equal to x over t. Solve for time. So I'll just flip it. So that's like 2x over v is equal to t.